ranked 14 in the country. So we are one of the best university in the Eastern India, and amongst the young universities less than 25 years, because we got the university status in 2006. So over a period of 15 years, we have gone to that ranking. So it is a all dedicated effort to our president, the founder president, and all the VCs, those are before me. I, being a man of medical profession, has spent almost 42 years at AIMS Delhi, and we wanted to, of course, develop many things in medical science. But currently, in last few years, what we have done, we have started medical technology. We have started super specialization like cardiac surgery, neurosurgery, oncosurgery, oncology, urology, kidney transplant, liver transplant, bone marrow transplant. This has happened in last 3 or 4 years. We are the only hospital which managed 660 beds in COVID, and we have 250 bedded ICU, and treated over 30,000 patients during phase and phase 2 or wave 1 and wave 2. So we have been doing good work, and it is with that we get about 4,000 patients every day in our OPDs. But coming to our academics, in last few years, we have started our wellness center. We have started the SOYA University fortnight lecture. We have started weekly institutional lecture, because we have 9 institutions, 36 research laboratories, and 15 deans. So every institution have a weekly lecture, and SOYA University has a fortnight lecture, and we have a wellness center. Excluding that, we have started Prachin, which is supposed to preserve, restore, and propagate the Indian manuscripts. So in that way, we have started doing something on old manuscript, which has to be preserved and restored. We have also started Indian knowledge system, and we have recently started human value, where we have told all our sister institutions to inculcate human value in all curriculum and as a phased manner, including 8 modules. And today we are here, and I thank Dr. Acharya to take Professor Manna.
Muted, Dr. Mahapatra, you are muted. Suddenly you got muted. I don't know why.
Oh.
You have to unmute yourself.
Oh, okay. So I have gone through the biodata of Professor Manna. It is very impressive, and he has a very long and academic career. So we are all looking forward for the first lecture or founding lecturer of our university. It's an opportunity for all of us, and let us hear and learn something from him. Thank you very, very much, and welcome to Professor Manna for the first lecture. Thank you, Manna.
Professor Acharya, Professor Acharya, unmute yourself.
Yes, I have unmuted.
Okay.
So, may I now request Professor Suddhasatto Vasu, Director of actually IIMT Bhubanewar, who is also one of the partner in this lecture series, which will be running once, which will be definitely having one in every month and maybe 2 in a month. So may I request you, Professor Basu, please give us some idea about what type of work actually this IIMT is doing, in particular in the research front.
Thank you, Professor Damodar Acharya, former Director of IIT Kharagpur. Our today's chief guest, Professor Indranil Manna, Vice Chancellor, BIT Mesra, Dr. Ashok Mahapatra, VC Shiksha Anusandhan University, and dignitaries on the screen, and all the fellow colleagues who have joined through this webcast to this first INAE chapter, Bhubaneshwar chapter lecture, which will be given by none other than President of INAE, Professor Indranil Manna. And we are very fortunate that he has given us time today, and this lecture is happening now. And I must also congratulate Professor Damodar Acharya for taking initiative of the fellows that 16 fellows that we have in Bhubaneshwar to form a chapter and start activities. Only a few days back, I was discussing with Professor Manna, who was saying that not only the fellow members, but we can also have activities with the members of, there are members, student members or members of INAE, plus those who are even non-members, but student or doing PhD in different universities in Bhubaneshwar or around. There are so many educational institutes in Bhubaneshwar and around, whether it's a government or central government institute or a public or private institute. There are so many research institutes. And here we are here that for the first time, all the INAE members plus invited people or invited interested scientific or engineering community who are attending today's very important lecture by Professor Manna on science engineering synergy for sustainable growth. This is a nexus of science, engineering and technology, which is important for the success of a technology to be taken to the field. With this, remind us about Institute of Minerals and Metals Technology, where I am from. We are an institute under Council of Scientific and Industrial Research, established in 1964. It was known for a long time as a RRL, but in 2007 it was renamed justifiably in Odisha as the Institute of Minerals and Metals Technology, where we have almost 30 to 32% of mineral deposits of India in Odisha. Whether you talk about bauxite or talk about hematite, or you talk about coal, nickel, copper, zinc, all mineral are available here at in Odisha, and there are regular mining and mineral processing and extraction of metals, whether it's through electric arc furnace, blast furnace, or hydroelectrometallurgy is going on. And we are here today in the capital city of Odisha to support this whole ecosystem of metal material industry, mineral processing industry. So we were very well known for our mineral processing division, where we the unit operations of chemical engineering or mechanical engineering or metallurgical engineering, all we know that is important for beneficiation. And we have all the facilities from a bench scale to pilot scale to do all, whether it's a flotation technique or it's a pelletization or it's a spiral or it's a ball mill, a jaw crusher or shaker. We have in large scale in the pilot level of facilities, and we do a lot of work for the ferrous industry in this region, whether it's a Tata Steel or it's a Jindal's. We do a lot of work for aluminum industry, whether it's a Nalco, Vedanta or Hindalco. We do a lot of work for HZL Zinc or Hindustan Copper. I mean, you name it, we do. Of course, another important is coal. So we do a lot of coal characterization, coal beneficiation. We have a technology for high ash coal. All you know that Indian coal is a very high ash coal. So we have a technology for that developed jointly with NML, IMMT and Simfar Dhanbad. And more importantly, the beach sand, the monazite, where it contains not only thorium or uranium, which is what one of the product of IREL that they make it here. But also you get neodymium, you get dysprosium and many other product, zircon. All these we support through our mineral processing division. Then we have a very active hydroelectrometallurgy division where we do non-ferrous, most non-ferrous technologies for extractive metallurgy. And a very active division, and there are not many actually metallurgy or material science and engineering department in the at least in India. We know that they are engaged in hydroelectrometallurgy, because this is more or less people don't want to dirty their hand, but we have very active department and we work on that very actively. The very few university or IITs are today actually do such kind of activity. Then we have advanced material technology, where we have a pyrometallurgy, a lot of facilities. We have very good lab on plasma and plasma processing, plus coating, thermal barrier coating. And I am very fortunate that with Professor Manna, we have students here working jointly with me and Professor Manna towards his PhD degree. We have also a student of his who is being taken as a scientist, also working here and on laser processing. And so these are the things that are taking place in advanced material technology. We have environmental and sustainability division, where we actually, wherever mining is going on, you have to reclaim sites. Then there's air pollution, water pollution, and then waste or industrial waste to be processed. And there are a lot of industrial waste like sludge, fine slimes, and slag lying, and we know that there is a lot of iron value in it, and we can do process it on that. There's a lot of red mud lying. There's a lot of value in red mud, from titanium to iron to rare earth. There's a lot of value in fly ash. So we do a lot of activities in around that in our environmental and sustainability division, along with mineral processing and hydroelectrometallurgy. We have a material chemistry division, where we work on functionalization of the material and their application in energy storage and coating sort of work. And then we have Department of Project Engineering, where we do on pipeline transport. This is very important. We do have a pilot scale pipeline transport of 10-inch pipeline and 14-inch pipeline, about 400 meters of loop, where we develop with NMDC and a Ministry of Steel. And this is now being used by other company as well to have their iron ore tested for the transport properties, where you need to add some additives to lower the viscosity. At the same time, you need to see that there is no deposition of minerals on the pipeline while the transport is taking place. So we have developed certain technology like impedance, electrical impedance technology in terms of finding out the holdup in the pipeline. And many others like ion pellet for instrumentation. So we have a process engineering and instrumentation division which does this kind of work. So with this small introduction of our lab, and we generate a lot of external cash flow. We call it ECF in CSR term, that project that we get from outside, and most of the projects are from industrial project. So we get on an average, even in the COVID time last year, it was about 45 crore worth of external cash flow we generated last year. And so our general and 80% of it is from industry, very few from ministry and DST kind of thing. So people are very active, and we do work hand to hand with the industry, and we like to do that. And last but not the least, I want to just touch upon the societal work. We do support, we have recently created just a few days back, it is opened by the minister here, Common Research and Technology Development Hub for actually helping the MSMEs in this region, brass, bell metal, or coating, or chemical processes, or in the area of plastics. Every MSMEs in this region we want to help through this DSIR funded Common Research Technology Development Hub. And along with that, we have opened the incubation center, a Section 8 company, Intech, NRDC. And this Section 8 company, of course, for incubation center, we are being recognized by Startup Odisha as an incubation center. And we are currently incubating at least 6 companies in our incubation center, and few of them are doing extremely well in supplying mineral processing chemicals to Tata Steel and Vedanta, or in JSPL, JSW, and JSL. So with this brief introduction, our societal work that we do in CRTDH, our societal work that we are doing in Nabarangpur, some of the aspirational district in Orissa, Kandhamal, with our sister labs.
To cut down.
So our labs, and so with this I end, and I would request Professor Manna to take this forward. I request Professor Acharya to take this forward. Thank you for your time. Thank you.
Thank you, Professor Basu, for such a beautiful presentation on what IMMT is doing. Now, I will request our INAE President, Dr. Indranil Manna, and Vice Chancellor of BIT Misra to give his actually lecture. Maybe next 45 minutes will be yours. And I will also like to say, those who are really attending this one, please, whatever questions that you have, you put it on the chat box, and Professor Renu Sharma will really take it up one by one. Thank you so much. Professor Indranil Manna, please.
Yeah, good evening, Professor Acharya. First thing is that I think the organizers have to give me right to upload my slide. The organizer, whoever
yes,
is the
sir.
host.
It is. Yes, sir. Good evening, sir. It has been given, sir. You can upload.
No, I cannot upload. I mean, it's still not enabled. Anyway, meanwhile, I should better utilize the time. I hope it should come very quickly. So, first of all, thanks very much to Professor Acharya, Professor Mahapatra, and Professor Basu. You know, I started my career in Kharagpur way back in 1985. Professor Acharya was already a professor at that point of time. He was a dean, and I used to bother him quite a lot with my sponsored projects at that point of time. In fact, Professor Acharya was the real architect of the SRIC of IIT Kharagpur. Subsequently, he also rose to the position of the director of IIT Kharagpur. So I know him for decades and always have admired his organizational capacity and commitment to education and research. Professor Sudarsata Basu is a very good friend of mine. He already mentioned that we do work together on some areas. I heard the very impressive profile of Shiksha Anusandhan University from its Vice Chancellor. Certainly, it's one of the most emerging university. In fact, Bhubanewar is the fastest emerging university town or center for education and research in the Eastern India.
So on the right corner, you are having a presentation arrow upward on the right side.
This presentation arrow is still disabled. It's not enabled. I cannot upload. So when I click, I cannot upload. So let me also add one or two words on behalf of INAE. It gives me immense pleasure because today morning we had the 141st Governing Council, and I had the privilege of announcing that earlier we used to have 6 or 8 chapters, and with Bhubanewar we are going to now reach 12 chapters, 12 active chapters. So thanks to Professor Acharya and Professor Basu for reviving Bhubanewar chapter, and small is always. Yeah, I've now got the link.
Yes, sir.
Yeah, so it's always very important that INAE reaches out. We always maintain that INAE doesn't want to be seen as an exclusive club of very elitist group of people. INAE instead would like to reach out to as much as possible, particularly in the field of engineering and technology. And we have provisions to recognize talents at the university level, at the college level. In fact, we award 30 awards every year. We give 30 awards to innovative student project thesis. And these students who receive awards remain with us for the next 5 years as student members. We have provision of identifying talents at the young level. We call them young engineers, and all young engineers remain with us as young associates until the age of 45. We have awards scheme for innovation and entrepreneurship, and they need not be fellow. So through that also we recognize those who are concerned with innovation and entrepreneurship. So likewise, apart from fellowship, we have several other schemes wherein we would like to embrace as many as possible in the connected with the engineering and technology field. So let me now come to the core of my talk today. Upfront, I would like to acknowledge that this is not going to be a completely new lecture. I have delivered similar lectures to other institutions in India. But the main reason why I decided to persist with the same theme is because the relevance is not only very high, remains a priority today. So for the sake of the country and its economic growth, it is very important that we understand why is the synergy among the science, engineering and technology is so much important for the country's sustainable economic growth. The mistake we often do is that we tend to treat science, engineering and technology as separate entities, independent entities. Now, for example, I have a cartoon here first to begin with. Nobody actually knows whether the apple really fell on Isaac Newton's head. But what is certainly known and chronicled is the fact that he was the first scientist who questioned why should apple fall from the top and not fly into the air, go farther up. So that led to the formulation of the famous laws of gravity. And today we know that not only for placing a satellite into the orbit, even for any flying object or various other aerodynamic processes, the starting point always remains as the laws of gravity. It has touched also our lives by way of helping us to explain the various planetary motions and also evolution of matter in space. The next question is, if a scientist asks the fundamental question as to why, without worrying about whether it's relevant or not, then what is engineering? In my simple definition, engineering is know-how. For example, as far as the history goes, it was Da Vinci who first drew this sketch as the possible way of a flying machine. You know, birds flying in the sky always evoked emotions in mankind. Why can we not also fly like a bird? So Da Vinci's sketch actually was an engineering drawing. Of course, he was not successful to fly this craft, but he certainly made an attempt to translate the scientific knowledge and ask how we can enable ourselves to fly. But the success to flying had to wait for a few more decades and actually, I mean, few more centuries until the beginning of the 20th century when the Wright brothers were able to first make a flight with this kind of a machine for just about a few kilometers. But today we are in an era where we can fly from New Delhi to New York or New Delhi to Melbourne in flat 12 to 14 hours without a stop. And we fly at an altitude of something like 30 to 35,000 feet above the sea level. We are actually have also defied the gravity and gone into the space, and we are now very keen in foreseeable future to make a trip to moon and come back. So all these translation from know why to know how and eventually to know what sells in the market is the seamless translation from science, engineering and technology. And often it gives us a feeling as if this is the sequence. So first, the scientific knowledge or truth has to be discovered, then engineering invention should take place, and eventually it may translate into a technology. But this sequence is not really sacrosanct, because here is an example whereby one can actually prove that technology is equally important to prove that the science was right. So 1916, Einstein proposed the existence of gravitational wave, and it took humankind another precisely 100 years to be able to develop what is today known as LIGO, or Laser Interferometer Gravitational Wave Observatory, in which India also is a very active partner. So with the existence of LIGO, we were able to prove that gravitational wave, or the God's wave, indeed exist. So technology also helps to prove science. So it is not one way, and that is the reason why I have put this reversible sign. So they actually feed into each other. Now, so as I said, science typically is no why, and it usually it comes from curiosity or need-inspired act, and at times leads to a huge peak called a discovery. Engineering, on the other hand, produces certain implements, devices, or products through specific inventions. And with value additions and innovations, these know-how translates into a commercially viable technology. So science is know why, then engineering is know-how, and technology is know what sells in the market. So it's not just economy alone. There are questions of ethics, questions of environment, recyclability, and various other aspects. So the principal thesis why I insist on this reversible sign comes from the fact that if science, engineering, technology constitutes the three vertices of an equilateral triangle, then at the centroid we have society. And it is because of the society, these forces always propel one to the next stage. So if one pursues only the fundamental science, then a brightest example could be Niels Bohr or the planetary motion, though of course this eventually was proven not so correct, in fact were revised that the planetary orbital model actually should have provisions to imagine elliptical orbits as well, or non-spherical orbits. So, but then it laid the foundation of the planetary model, and whereby we came to know that matter is made up of atoms, which is the smallest unit possible, maintaining all the chemical nature, and the mass of the matter is concentrated, or the atom is concentrated in the nucleus with proton and neutron, and electrons orbit around. But that's discovery, certainly is a fundamental discovery, but nobody knew what to do with it. On the other hand, when Edison realized that by applying potential difference, you actually can make electrons flow along a conductor, his immediate intuition was that how to make use of that. So from Faraday to Edison is a seamless translation of fundamental knowledge into viable applications. So that is inspired research. And the combination of both, one of the brightest example could be Louis Pasteur, who was first to discover the role of penicillin, or discovered penicillin, which has not only the fundamental aspect, but also saved millions of people in years to follow. So academia creates or disseminates knowledge. That's what we always do. Either we teach or we develop new knowledge system by research. Research organizations, they pursue inventions, borrowing from the fundamental knowledge, and industry laps up these innovations and creates viable technology, which sells in the market. And this happens because there is a huge demand always from the society. The cell phone we are carrying today, we often believe that's the top of the shelf, the most recent one. We never know after 6 months whether the same device will be considered the most recent one. And that changes happen, not that everybody knows, everybody demands a cell phone which probably has just a few more functionalities. But the demand of the society always drives the companies to pursue better and better innovation. So this cycle continues, and this is the so-called modern innovation ecosystem, which is of course knowledge driven, and which is why this is a perpetual motion. So what is innovation? Typically, innovation means creation of a new idea or a new thoughts, some imagination, and which often leads to formation of a new device or a method. So usually innovation or development through innovation is incremental, always cross-disciplinary because it leads to a systematic solution, and directed and translational. So the innovation power is manifested through certain products or processes and is made successful through certain business models. Innovation is not per se the invention or discovery, but it certainly is related to or actually emanates from inventions and discoveries. And innovation is best suited to engineering and technology. And we have several bright examples throughout the world, through the ages, starting from Wright brothers, as I said, or quoted Edison's discovery. In recent times, Larry Page and Steve Jobs and so on and so forth. And not to forget the one in red, Prafulla Chandra Ray. But before I come to PC Ray, I would like to mention that despite being a country of huge population and potential, in terms of global innovation index, India is doing better, but much smaller, much lower than what is expected. We are in terms of the number of nations, something like about 170, 180 countries, we are only at the 48th position. But then this is still within top 50. But then 50th nation is Philippines. So if you compare the size and the might of these two nations, you always would realize that we have miles to go. So the question is that what is needed to make us a more innovative nation? We need knowledge. We need translation of knowledge. But there India ranks 27th in knowledge and technology outputs. This is again better than the last decade, but is certainly not what it should be. So here is an example. Often we talk about innovation cells, entrepreneurship park, and so on. Little do we realize that the first chronicled example of translation of knowledge into a product from lab to technology, commercialized technology, perhaps in India, was the innovation of mercurous nitrite and nitrate by Acharya Prafulla Chandra Ray. So he was trained as a chemist, obtained his PhD, and was very well known professor, in fact, very prestigious Palit professor those days of Science College, had number of publication and was already well known as a chemist. He was also made the president of Indian Science Congresses in 1920. But something actually bugged him, and he realized that while science should be pursued in the labs, there should be the fruits of science should reach the common masses. So he founded Bengal Chemicals and Pharmaceuticals, India's first example of lab-based knowledge translated into a commercial product. And of course, those who know Calcutta a little bit would recall, not now, decades ago, Bengal Chemicals, it still exists, but Bengal Chemicals used to be one of the biggest industry in Calcutta. Now, what is the power of innovation? For a while, if you refer to this particular very famous book authored by Arthur Clarke, it talks about certain innovations that change the face of the 20th century. So if you have to define the greatest innovations that change the life of common masses, then here are the examples. I mean, can you think of the 20th century without electricity, without automobile, aeroplane, very many things, personal computers, telephone. So all these things, even internet came into existence, various imaging processes, nuclear technologies, various high performance materials, and so on and so forth. So these are just 20 examples. Of course, one can argue that with another 21st or 22nd example, but nevertheless, these are brightest examples what changed the face of the humanity during the 20th century. Now, here are also some other examples. For example, the 10 best technology innovations during 19th century, and now what is happening in the 20th century, which are basically the top innovations which are happening. These are not yet mature. Internet of Things. I mean, you not only need an internet to communicate between PCs, but also between physical objects. Artificial intelligence. In many cases, you actually are going ahead of the human brain, and without tasking the human individuals, you're able to not only make decisions, you're also able to come up with new knowledge and new directions. 5G based communication devices, blockchain management, various robotic devices, biometrics and biomimetics, additive manufacturing, and so on and so forth. So these are the indicators as to how innovation is going to change the face of the 21st century. Now, the question is, why is it that the possibilities that we encounter or develop in the laboratory, why is it that all the time each one of them does not reach the final success? It doesn't reach the final success because of the so-called famous or infamous valley of death. What does it mean? That we wish that the path from fundamental knowledge or applied knowledge to reach the product could have been something like a straight line or a path which is on a plain land like this. But in reality, it always goes through a valley before it reaches the peak. And during the valley, you have stages of research. So during the early period, you'll have research and development, and subsequently there'll be certain strategies of marketing and feedback taking. So then you have to go through the most difficult part, which is the hurdle of commercialization. And eventually, once you are able to commercialize, then of course you reap the benefit. And that's when you approach the peak. So the survivability threshold is actually a much longer time than the final success period. And this is the crucial time when one actually not only will have to be very patient, but also be extremely innovative and resourceful. Now, resource and innovation, they actually should combine in the following way. So on one hand, we have resources in terms of knowledge, manpower, maybe finance, maybe various infrastructure. So with time, as the stages of development proceeds, the research resources actually basically decrease substantially. And instead, what comes up or pops up is the commercialization possibility or the prospect. So these two basically have completely different curvature, and one is in the descent, the other one is in the ascent, and the job is to bridge these two gaps. But this so-called valley of death or the gap is actually, one can deconvolute and realize that may have multiple stages. So maybe there are it's not a one single valley of death, probably it has the first death, the second death, or the third and fourth, various traps. So what are these traps? You need to translate basic research to spin out or spin off to developmental stage, to demonstration, to deployment. And by the time you reach the deployment, you are already approaching the peak. Now, typical success rate, if you count the number of innovations patented and the number of patents commercialized, you'll realize that success rate is not even 10%, hardly a few percent. So that is exactly why it is very important to be not only aware of the valley of death, but also have certain strategies as to how to build this bridge so that one can move to the other part. So as I said, technology is know what sells. So what determines that sellability? Is it price, the economy, the performance, efficiency, availability of material or supply, the superiority in terms of properties, the level of investments, or sometimes simply ethics, the visual appeal, the ethical issues, and so on and so forth. There are many, many questions. So if sustainability is the ability to maintain the desired rate or level, avoiding the depletion of resources, energy, and disturbing the related ecosystem, then one must agree that sustainability is a composite concept. So there is no one single linear formula. So one has to be innovative every time at every step. And also it is not time independent. It also depends on geography because law of the land varies from one country to another. So engineers and engineering, they actually have to be quite competent and be able to handle the sustainability issues. Now, we also have to realize that the core of engineering lies in translating fundamental concepts to design, develop, fabrication, exploit various other elemental concepts. So that means we in engineering not only should talk about the basic equation like law of gravity, but we should also teach about how to design a rocket or a device which can defy the law of gravity, or what happens to a certain mass when it is pulled through gravity and impacts on a certain hard object. So we know very well that in present era, the typical sustainability challenges are related to energy, water, and of course, key materials, including steel and rare earth and so on. So the United Nations actually has identified 17 specific sustainable developmental goals, and these are related to the economic condition or poverty, hunger, health, education, gender equality, water and sanitation, energy, and so on and so forth. Each one of them actually can be further brought down to multiple themes and topics and specific directions. And that means that one chapter, let's say affordable clean energy, will have multiple sections and subsections. And it is up to the academic and engineering and peer bodies like Academy of Engineering to decipher the challenges under each of these chapters and then bring it to the notice of the engineering personnels and professionals and throw challenges at them so that eventually some solution emerges. So we have to worry about the societal need and aspiration. We have to be aware of the economy, ecology, and growth conditions. We should be completely in the know of the resources available, energy and environmental issues. So when we address all of them, then we are addressing the reliability concept, the profitability concept, feasibility concept, so that eventually we reach the sustainable growth targets. At the interface between the 20th and 21st century, United States created a special committee to define what they call the grand challenges of engineering. So National Academy of Engineering USA was tasked to identify specific targets or questions that should be addressed during the 21st century so that the entire population, the entire humanity can actually have a much better quality of life. So it was a very exclusive committee with the former Secretary of State as the chair, with 50 subject experts from 40 different countries. And eventually, hello?
Please switch off your microphone, all those users. Please switch off your microphone, please.
Okay. So there's National Academy of Engineering defined these 14 grand challenges, and these were specific themes like how to manage the nitrogen cycle, or how to make the solar energy more affordable, and so on and so forth. So around that time, India through the TIFAC also created the technology vision. Dr. Anil Kakotkar was a chair, and they also came up with some specific themes, but they were fairly broad based. And at that point of time, 2014 precisely, Government of India created a task force with all the directors of IITs, and we were charged with the responsibility to create how should India tackle the future engineering challenges. So we created, it's a long history, just in one word, one may say that we went through more than a year-long deliberations, and eventually were able to come up and proposed a program called Impacting Research, Innovation and Technology. Professor Acharya mentioned about that. So this imprint program was steered by Ministry of Human Resource Development at that point of time, alongside DST. So the outlay was about 500 crores to begin with. It was much larger. Eventually, it was pruned to about 500 crore. And what is very unique about imprint is To the best of my knowledge, this country doesn't have many examples where the topmost leadership of the country, the Prime Minister and the President, they decided to launch a scientific program leading to, of course, aiming innovation from the Darbar Hall of Rashtrapati Bhavan. And this was November 5th, 2015. So there were 10 themes, 10 domains created, and they were all, you can realize, they are not mechanical, electrical, and so on. They are, for example, healthcare technology, because we all would agree that system-based solution requires input from all disciplines from 360-degree view. So obviously they cannot be one engineering specific, but targeted towards a particular sustainable solution. So we had 10 such domains. Each domain had 10 themes. Each of the 10 themes had targets and topics. So that makes it 10 raised to 4. And for each of these targets or topics, there could be easily 100 variants, because geographically or through geographical variation or perception wise, there can be various ways of approaching the same solution. At times, I think, I don't know how it's happening, but anyway, let me go ahead. So essentially, what I mean is that we defined 10 domains, but eventually realized that these 10 domains are going to encompass something like 10 raised to 6 million challenges. So, but then we also put up a brave face and we said, million challenges, all right, but we have billion minds in the country. So it should be quite possible to handle those challenges. But what was profound was that when we said that we are going to use Imprint as a model, as a platform to synergize with all other major governmental initiatives, be it Clean Ganga or Rashtriya Avishkar Abhiyan or Skill India, Digital India, and so on, the Prime Minister made a comment at the launch, which I personally thought was very profound. He said, science can be universal and should be universal. It should address not just India or one region of the globe, but the world over. But engineering solutions must be local, because the local aspirations have to be respected and addressed to. And with that perspective in our mind, we went ahead. So I'll fast track here. So from 2015, November 2020, I happened to be the national coordinator for 5 years. So before I completed my term, so we had the privilege of meeting in IIT Delhi in August 2020, where we actually showcased the major innovations. I'm sorry, not 2020, 2019, where we showcased the major innovations that took place under Imprint. And here are some examples. For example, handheld devices, point of care devices for glycemic control, HbA1c measurement directly. Creation of artificial pancreas through lab-based innovations, hemoglobin detection through micro devices, microfluidic devices. Similarly, measurement of various particle sizes and distribution, also impurities and air pollutants and so on. And so essentially, Imprint, in my opinion, was the first example where the academic institutions, all the IITs, IISc, and top institutions in the country came together to pursue a single goal of providing sustainable solution to engineering challenges. And all other institutions, government or non-government, industry, all were made partners. Imprint had Imprint 1 and Imprint 2, 2 phases, and also different stages. The total outlay actually by now should have crossed 1,000 crore, and more than 300 institutions in the country were involved. So with this, I now would like to spend the rest 10-12 minutes on providing you examples of innovation that has taken place in a laboratory. Professor Basu belongs to CSIR IMMT Bhubanewar. I had the privilege of working in CSIR laboratory in Calcutta called Glass and Ceramics Laboratory. It has a checkered history because none other than Meghnad Saha realized that India would require quality glass, optics, and lenses when it has to pursue post-independence development. And eventually, I don't know whether he actually envisaged, but this laboratory also created specialty glass, even fibers, optical fibers. So 1950 it started its journey, and I'm going to take 3 examples as to how this laboratory-based innovations actually has helped the country. So this is the view of the Tarapur center, hot cell room. So behind this particular wall, you have everything radioactive. So you cannot ever, never, ever you can enter into the room. And all the nuclear fuel, they are processed, they are encapsulated inside this room. So the operator has to see and then handle using, of course, remote handling devices. But if anything goes wrong, or if anything is not on track, then the operator should be able to see and locate. So you need not only a radiation shielding wall, you also need a window. And that window has to have a special property which will allow to stop not only alpha and beta rays, but also gamma ray, the most penetrating one, having the shortest wavelength. So in order to stop gamma ray penetrating this window, you require, and also you require a transparent window. So you require glass. If it's a borosilicate glass, then you require almost a meter wide, because its absorption cross section is high, but because of low density, you require almost a meter wide or meter thick wall. And a meter thick glass, those who are familiar with glass melting would realize that it's practically impossible to create a single glass object which is meter long width with no stria, no other refractive index variation. And you can't change it halfway through. I mean, once it is sealed, means it's sealed forever. So it took precisely 40 years for CGCRI to master this technology. And it was started by none other than Atmaram, the first director of the lab. It was just started. You'll be surprised to know that this project, if this project costs 100 crore, 75 crore of that project is spent on only one item, and that is the crucible in which you melt the glass. And that crucible is made up of nothing other than pure platinum. So you require, just imagine, to create this window, you require a special glass which is high silica and high lead oxide, I'm sorry, and it's so corrosive that only platinum can withstand this corrosive attack at high temperature. So it took, as I said, 40 years nearly, and eventually I was fortunate during my time, we could fulfill this supply to atomic energy and fulfill the initial contract. CGCRI also created this the boosters. You know, today we all use optical fiber for communication. You need to boost the signal at various nodes, otherwise the signal decays through natural attenuation, and you cannot hear the voice, or the signal doesn't reach the endpoint. So you need accelerators time to time, and so this was created. This amplifier was created in CGCRI and commercialized. The first example in the country. CGCRI developed end-to-end technology for converting preforms, optical fiber preforms, and draw them into, so something like you start with 10 centimeter diameter preform, and eventually you draw 10 micrometer thin fiber. So you can imagine you're talking about essentially more than 1 million order of magnitude difference. So from 10 centimeter to 10 micrometer. So this fiber also will have a core which has a refractive index of such value that light, when launched in that core, will not be able to come out of that internal core. So the outer core is only, which actually constitutes 80% of the diameter, but the 20% of the inner core is a specially devised composition, so that only the optical ray launched from one end will remain completely embedded within, and by total internal reflection, it will never be able to leave the core. So CGCRI not only created this fiber technology, but also created this fiber Bragg grating, which is used for very many structural health monitoring, including the health monitoring of bridges, roads, buildings, and these towers, these long, tall towers that we see for high voltage power transmission. CGCRI also created a super continuum source. So this is nothing but, again, another innovation happening in the lab, and eventually a 39-watt super continuum source, first time in the country and third in the world, which was marketed through a company owned by an Indian but based in US. So in addition, now is the third example. So optical fiber, specialty glass, optical fiber, and now hip joint prosthesis. I'll straight come to the point that at that point of time, this device in 2011-12 would cost 30,000 rupees. The same hip joint in the market, which is sold by a foreign company, would cost 1.5 lakhs. And more than 100 patients actually were given this benefit of, here is a patient who got benefit from this particular device. And this this device was implanted by Dr. K.H. Sancheti, possibly the most well-known orthopedic surgeon at that point of time. CGCRI received technology award and all that. And I must mention that the key inventor here, Dr. Devbrata Basu, is no more. And he had a missionary zeal. I mean, despite his failing health, eventually he passed away at a very young age. But he was a key architect and made sure that this device reaches the market. Now, this is why I spent 5 minutes on explaining the value of death. So many people often say that the scientists don't understand the market language, which is to a large extent true. But even after reaching the market, even after CGCRI transferred these technologies to one company, US-based, another company, India-based, and Atomic Energy for some other technology, many of these are still not selling in the market and certainly not being able to compete with the might of the multinational companies from abroad. So it is not enough that we understand only law of gravity. It's also important that while we train engineers, we also train them the way how to overcome these value of death. But of course, an individual cannot do much here. The government machinery and law enforcement agencies, and more importantly, the society as a whole also have to work together. I would like to give a very simple, down-to-earth example. Something called Ukrainian clay. I don't know if in the audience we have anybody from refractory field, because Odisha is very well known for refractories. So a particular tile, ceramic tile, required about 40%, 25 to 40% imported clay called Ukrainian clay. And why was that important? Because if you use local clay, which contains iron oxide, when you fire, it forms a low melting eutectic and it tarnishes, it creates a reddish glow. So the milky white tiles are not possible using local clay. So our technicians, not scientists, in CGCRI center in Gandhinagar in Gujarat, they were able to show that if you use a particular acid leaching technique, then you are able to leach the iron oxide away, and then the remaining clay can very well be used for creating such high-end tiles. So with this kind of small intervention, we used to have only 14 companies in 2005. That rose to 64 companies in 2011. And each company started making profit margin, raising its profit margin by 6-fold, 3.5 crore per annum per unit per year. So a single intervention, and this is why I'm taking this example, that innovation is not necessarily always a rocket science. Innovation could be fairly simple, common sense based, but very effective. And that increment can make all the difference to compete with an international product and make it and do it at a much cheaper and a much more effective way. So translational research is important, but then we often say that in academia, this is always a far cry. In fact, I often acknowledge that in my small stint in CSIR, if anybody asks me, what did you learn? I would simply answer that the difference between the technique and the technology. So in academia, we have the habit of always claiming when we create a small device, which is probably a 1 centimeter or maybe a few millimeter or a few micrometer, and we derive properties which actually could be even better than what is already published. So we immediately proclaim, Eureka, I found something which is better, and we start claiming that I have created a technology. And this is where we make the biggest mistake. The same thing when from 1 micrometer, when it is to be taken to 1 meter or from 1 kg to 1 ton, it is not just arithmetic addition. You actually now require a completely different setup and a completely different approach. So it is not just simply arithmetic scaling up, it is now a completely different mindset and approach. And this is where the translational activities often perish. So, of course, we need, for technology development, we have to understand it's a painstaking job, very time consuming. Often it has risk of failure. We require infrastructure which is often not available. Whatever is possible for micrometer scale cannot be easily translated to meter scale or cannot be tested. So we require different infrastructure. The rules, regulation systems often are not conducive. We face a lot of difficulties in terms of the initiative and the output that happens. It's not always quantifiable. You cannot show I published so many papers. In fact, a person who is working in a lab and pursuing a very high-end technology may not be able to show any output at all in maybe years together. But we have to persist with that person if we really want an output. The translational effort is always a team effort. So at the end, it becomes a problem that only the managing director receives the award or the person down the line who actually have contributed. Then the commercialization mechanism is difficult to follow. And we often carry a very wrong notion in India that Saraswati and Lakshmi are actually very bad sisters who fight with each other. And we also believe that it is actually a sin for an academic to aspire to be rich one day. So these mindsets also have to be changed. So in my opinion, these are my own prescriptions as to what needs to be done, why the collaboration between industry and academia is practically non-existent or is so evasive. So what needs to be done? I mean, I would rather skip this part, but what we need actually, this is what I would like to stress upon. What we need is a few, few success story which creates credibility, confidence, and respect for the not just academic community, but research community. So I'll take 2 more minutes to drive home another very important point before I wind up. When we talk of India, we must first and foremost, we must realize that we are talking not about a monolith. We are not talking about one single composition and one single solid entity. We are talking about a composite, a fabric, a very complex fabric, which in the words of Tagore is nothing but a unity in diversity. Every 100 kilometers we travel, from the language, food habit, religion, texture of the person, appearance, dress habit, marriage code, everything changes. So this for about say 3,000 kilometers north-south or east-west, we have very many small countries, but they all are interwoven into a common fabric. So when we want to produce a solution for the country, we first have to understand what is the country we are talking about. I mean, we have 5,000 years of chronicles history. We start from Conrad, who actually wrote certain scriptures describing the planetary motion. We have geniuses like Ramanujam or Satyam Bose, and recent times Ashok Sen and so on. But is that enough that we only bask in the glory of the past, or should we not realize what is the ground reality? So on one hand, we have reasons to be very proud of our history. As I said, more than 5,000 years of chronicle history. And this is also a fact, it's not a fiction, that until the beginning of the 18th century or the end of the 18th century, India used to be one of the richest civilizations in the world. And what happened afterwards is something to be understood. more than blaming the foreign power, we should first do a soul searching and realize as to why we allowed this thing to happen to us, that from one of the richest nations in the world, where 20% of the entire world's GDP used to be supplied by India, and today not even 2% we supply to the rest of the world. We are one of the largest country in terms of geographical area, huge expanse north-south. We have a huge coastline. Population right now is 1.4 billion or slightly more, second most populous state. But more than this figure, what is more important is the figure that more than 800 million of these 1.4 billion is below the age of 35 years. And we possibly today happen to be the youngest nation in the world, even ahead of China. So obviously, if India has one dividend, that this is this particular young population, which we have to learn how to harness. The GDP is a very respectable figure, sixth in terms of nominal and third in terms of purchase power parity. The science and technology wise, we have reasons to be proud that we could launch the lunar mission, Mars mission at the cheapest price possible, satellite launching capability, nuclear energy harnessing state. We have managed to reach nearly the same level of life expectancy today as the world average. We have very many large companies, for example, railways, which is the largest employer in the world. And India's civil aviation market today is 9th, but is growing and may soon overtake many other countries. So we have a huge market. But on the flip side, as I said, we have a huge diversity, 37 states and union territories, 22 official languages, maybe 29 official languages, and 8 main religions. Name anything in the world, it exists in India. And the biggest point of worry is the per capita income wise. We are 167th nation in the world out of about 180 or 190 nations. We have about 22% of the population still below poverty. Human Development Index wise, we are the last in the G20 nations. Unemployment is 6 to 7%. Gross enrollment is probably better than 20% now, but is far less than what it should be. We have challenges in poverty, hunger, healthcare, security, everywhere. We have a huge balance of trade because nearly 100 billion per year is the deficit. And we certainly lack in infrastructure and amenities. So engineering solutions are awaited for energy, defense, water, education in almost every sphere. Now, one other very important puzzle we must realize is the puzzle about Indian economy. If you look at this green side of the pie chart, 53% of the population is connected or employed in agriculture, engaged in agriculture. But they contribute only 14% of the GDP. On the other hand, 59% of the GDP is contributed, this yellow part, is contributed by the service sector. And service sector, without casting any aspersion, can be one can wind up in no time and be left with no asset value. It doesn't create asset. It does create services, it does create jobs and wealth, but not necessarily asset. So this is not a sustainable model that more than half of the population is engaged in only 14% of the GDP or the employment generation or economic activity, whereas more than half is actually coming from a sector which is fairly transient. So this puzzle needs to be solved, understood, and in my opinion, the best think tank for that to pursue will be Indian National Academy of Engineering. So I'll end up with these few lines here, and please allow me to actually read through, because it's important that we understand each and every word. Science is pursuing the truth relentlessly, regardless of its necessity or immediate scope of application. Science provides clues, if not answers. Science extends as far as imagination goes. Science never fails, but some scientists can. Engineering is all about enabling and providing solutions, borrowing from the fundamentals of science. And technology is the last mile for societal benefit, based on scientific discovery and engineering inventions and innovations. So let us ensure that science, engineering, and technology in India complement each other and flourish together so that our society soon achieves the desired culture, growth, and prosperity. If India has one unique resource and strength that the entire world envies, that certainly is the demographic dividend, the youth. Engineering can ensure self-reliance and self-esteem. So it is to this end, I must say that it is our sacred duty to understand the power of knowledge, which actually transcends from information to data to knowledge to eventually wisdom. And to pursue knowledge, you have to emphasize on education like never before. But this education, in the words of Confucius, should be not filling of a pail, but kindling of a flame. So the knowledge should actually uncover and not cover through idea and imagination. So yes, we must have ambition, but not without ethics and accountability. Success comes quietly without chasing, without your chasing it consciously. The governance has an important role, a pivotal role, because you may have all the ingredients, but you as an individual cannot do much unless the system allows you to pursue. And education is the bedrock and lays foundation to sustainable and societal and economic growth. So to that end, we have to create the synergy, and we have to look at the centroid, borrowing from the wisdom, knowledge, data, and information. And that's how we can proceed in the future. And research is the key because it never begins, never ends. I mean, many times the research scholars ask, sir, where should I begin this particular work? I said, you are beginning by you, but this beginning has already been made by very many in the past. So one has to understand that it never ends, never begins, it continues. And solutions often are not unique. They can be manifold. So sustainable growth demands multidisciplinary scientific approach. So with this, I'll stop and thank you for your kind attention. And I hope I could make some sense to you.
Thank you, Professor Manna. It was excellent and stimulating. It will encourage us to have many more such, webinars. And now, may I request Madam Renu Sharma to put actually some questions to Professor Manna from whatever that she has got from the charts.
Thank you, sir. Thank you so much, sir. One question from Professor R.K. Bhandari. Sir has written your stewardship of imprint in its informative stage was commendable. Has it's measured up to the national expectation? What are the 2 or 3 most significant lesson learned so far?
See, Dr. Bhandari is one of those peers who we have grown seeing peers like him. So obviously he understands the challenges certainly much better than I do. But one major takeaway, Dr. Bhandari, in my opinion, is that today people are not only aspiring, they are demanding. So I would say that the educational sector has to adapt and create an environment where education is not just teaching based, not just pedagogy lectures, but learning based. So we have to allow students to make mistakes and learn through mistakes. In other words, learning through project-based education. I think national education policy does talk about that, but I don't think implementation is going to be very easy because we have very many constraints. I think we have to somehow instill confidence in the youth that they can do it. So, I mean, that's one important takeaway I imagine is required.
Okay. Bhabani, sir, want to ask some question. Sir, please. Bhabani Sinha, sir.
Yeah. This is Bhavani Sinha. I am actually from the INAE Kolkata chapter from Indian Statistical Institute, but now I am in the SOA University. Yeah. So first of all, I would like to thank Professor Manna for a very insightful, detailed talk, knowledge about all these transformation from this particular engineering to technology. And I, from the core of my heart, I also sincerely feel that these are very useful for the development of this entrepreneurship and the overall development of our country. So I just wonder whether is there any effort to include all of your concepts, such as value of death or how to overcome those things in real life with some specific examples, particularly engineering specific some examples in our curriculum, so that the youngsters can have beforehand some idea, if those who have some aspiration for becoming an entrepreneur, so they can be well conversant about these problems and how to solve in typical cases. So is there any effort from our, higher level educational policy or anything like that? Do you know? So I just want to have that idea.
I think I'm authorized to speak on behalf of INAE more than any other organization. So I'll confine myself to INAE. As I mentioned, we are very keen today to promote innovation at all scale. For example, when we give Innovative Student Project Award, we don't necessarily give that award to the topper of the batch, not by the grades or the score, but by what innovative idea one has demonstrated in the thesis. Similarly, when we look for an individual for Young Engineer Award, there again, we say that the scientific contribution is very important, we don't deny, but we are looking for the engineering component. So essentially what we mean is that fundamental science has to be pursued and has to be even strengthened, but we are looking for evidences. We are looking for translation which either shows the promise or already has demonstrated up to a certain level. I mean, so-called technology transfer level 6 and above. Also one other point you may be aware of, something called Kalam Fellowship. Department of Science and Technology has a very prestigious fellowship called J.C. Bose Fellowship. Essentially for those who have made it, who are very eminent in terms of scientific contributions. So INAE pleaded with TST and eventually got a new fellowship scheme approved and implemented called APJ Abdul Kalam Fellowship. And Kalam Fellowship, in terms of remuneration, facilities, and so on, is equivalent to J.C. Bose Fellowship. But you'll be surprised, Kalam Fellowship awardees, there's a difference. Kalam Fellowship is only once, not continuity, and cannot be continued, only once. And that too in 3+2 model. So you write a proposal. If the proposal is accepted by the committee, then you're given the fellowship, you work for 3 years, come for a midterm review, and if you are going in the right direction, then the committee allows you to proceed for 2 more years. So essentially, we are trying to create a culture which is result-oriented and product-based, right? So the prestige-wise, remuneration-wise, it should be equivalent to J.C. Bose Fellowship, but will be given to you only when you show a promise of a product. And who have been awarded, many times who are already very eminent, but also we have given, I can cite one example, an associate professor who is into the profession for the last maybe 10, 15 years, but proposed something which is basically UAV, unmanned aerial vehicle, and with certain innovation which could be applied for various weather prediction and so on. So we thought here is a possibility of innovation reaching a particular product state. And we gave him this fellowship. And during the midterm review, everybody was so pleased that he has made such important inroads already. So it is not by counting your papers or your already achieved biodata, but because of the promise for a translation. So these are a few examples that I may cite where INAE is trying very hard to promote innovation culture.
Okay, thank you. I was wondering about, teaching these youngsters about these problems in this translation and to make that part. So,
One other thing, let me tell you that we often talk about science and entrepreneurship part, step. Professor Acharya would recall IIT Kharagpur has one very active one. But when I joined BIT Mestra, to my surprise, I realized that even a private institution like BIT Mestra was first in the country to create something called STEP way back in 1974. So, I mean, it's not that what we are doing, for example, imprint, of course, at times we claim that this is the first of its kind initiative, but I'm sure there were similar initiatives in a smaller scale in other places. But imprint was first to actually address the entire engineering domain. So likewise, I'm saying, yes, in curriculum, we should bring in more of design components, more of practical project-oriented work where somebody creates a new design of a bicycle, for example, or make some solar device more efficient, or somewhat like. Yeah, I hope I could convey.
yeah.
Yes, Professor Manna.
Thank you very much, Professor Manna. Okay.
Professor Manna, actually, this BIT Mesra Science Park
Right.
is perhaps the first in the country, and it was promoted by one of the faculty from IIT Kharagpur, Professor Ajay Bose.
Oh, okay. Okay.
So there is another question from Dr. Narsimhacharya. Sir, how can we improve agriculture sector as a large percentage of the people are working, and how can we improve revenue generation?
Of course, I don't think I'm competent to give a comprehensive answer, but let me try from whatever little I know. Agriculture in India still continues to be pursued to a large extent in a traditional way. IIT Kharagpur is the only IIT in the country which has an agricultural engineering program, but I don't think agricultural engineering has been very effectively implemented throughout the country. I mean, of course, we have ICAR and other organizations who make a lot of efforts. For example, still we know that irrigation is a major issue in terms of agriculture. And one of the biggest source of wastage of precious resource called water happens through unlimited irrigation or unwanted irrigation. Now, proper sensor-based monitoring of how much is the humidity or the hydration level of the soil, and accordingly monitor and implement so much of watering of the soil is still not implemented in many places. I've seen in my own eyes what Israel has done through drip irrigation in such wide saline land. But in India, we have places in the south where water retention is a major problem. We have places in the east where the soil is not only fertile but also can retain a lot of moisture and water. But this is just one example. Similarly, of course, Green Revolution is one major achievement which has made the country proud. But I personally feel that agriculture sector is one area where a lot of possibilities exist, where engineering can certainly make a huge difference in terms of crop production, crop planning, rotation, food preservation, food processing, and many other aspects where engineering is more important than the basic science.
Thank you, sir. Sir, we would like to take some more question, or will be done?
No, I'm okay, but I think people probably by now should be surfeit of all these. I can very well take one or two more questions.
Last question, sir, I would ask. It is from Manisha Rath. Respected sir, I am Manisha Rath, MSc Chemistry student from IIT BBS. I wanted to learn that is there any current research going on porous metalled roads which can reduce waterlogging and increase groundwater levels?
Well, this is typically to be, I think I would expect some transportation engineer, pavement engineer to talk about that. But if you ask about porous solids, yes, there is certainly a lot of developments, but not to my knowledge, enough is done in terms of roads with controlled porosity to absorb the excessive rainwater. But rainwater absorption through road is not the right approach in my scientific understanding. We have to have immediate drainage system. And obviously the soil condition, the slope, and the weather condition at that point of time, all these factors have to be taken into account. But to the best of my knowledge, I cannot be 100% sure, but I don't think there is any major project in the country where the road itself is planned to be made porous so that it can absorb rainwater. I'm sure there are many civil engineers in the audience who would know better than I do.
Thank you, sir. Over to Professor Damodar Acharya, sir.
I have a question. If I allowed one question, Professor Acharya.
Yes, please.
My question is the previous discussion that was going on about the innovation. Do you think, Professor Manna, that innovation is something, an innate quality in a human being, which possibly cannot be taught? And the culture of copying is very much instilled in India. So first question is it something which can be taught? Or is it through the IPR route that you make people aware of the protection of innovation and then say people that if you have to do something, you have to actually do on your own something new, then only you come to the market? I mean, what is the way forward for Indian people or India to have the student, among the student, this innovation, create an awareness or how to innovate? Or, I mean, I know it's an innate quality, but what can be done for India? I mean, we are instinctively kind of copy many things, and there was no bar here, there was no law regarding protection, although today we are much more aware of IPR. So your thought on that?
Vivekananda said many centuries ago, the education is a perfection of man already existing in it. You need education only to hone the skills. So you're right, innovation is an attitude which probably exists in every individual. When I said education not through the teaching model but through learning model, that is what exactly, in my opinion, is necessary, which will allow somebody to discover oneself. So you and I may be endowed with certain potential, but unless you create the right environment, I'll never know that I could also sing well. I've always believed that I'm a very poor singer. But maybe someday, somewhere, I come across an environment which encourages me to try it out, and I may end up being a good singer. So all I'm saying is that you have to enable, you have to create an enabling environment for somebody to try out. The biggest mistake we do in our society, and in fact, all of us are equally to share the blame, is that we all believe one size fits all. So everybody has to be either a doctor or an engineer and must score 99 out of 100, and and so on and so forth. So somebody who probably has an enormous potential to be an excellent, let's say, painter, is forced to pursue a career to be a mathematician. And by the time that individual loses all appetite, in a few years' time, the guy will be left with no power of imagination or aspiration, leave alone innovation. So we have to create the right enabling environment and look for the look for the talent, or look for the evidences, or some bit of examples, so that we know he is good at that and he should be promoted in that direction.
Okay, Professor Manna, I will just take 2 minutes in answering some questions which were raised here. First of all, First question I will take is actually one girl who said that whether actually roads we can make porous. The real enemy for the road is actually the rain. It is water is the enemy for road. So you cannot really allow water to be the road to be porous so that it can really get into the soil through road. In fact, the simple thing is that if you can have the road constructed, the pavement has to be so designed that it is just like the back of a tortoise, then water will not be there. And it is only the, drains actually who can take the water out. But in fact, what we do is just ulta. We actually design always road come drain. That's why actually this creates such a lot of actually problem for us. Second one, which was posed here related to agriculture, I may just say here, ICRIST in this that is actually in Hyderabad, International Center for Research in Arid Climates. They have developed actually a technology which we may call it some sort of smart agriculture technology, where they are using like starting from actually remote sensing to IoT to artificial intelligence and all these things to make sure how the productivity from the agriculture things could be improved and how real-time information could be provided to the farmers to improve their actually practice. And this is being implemented in one district, that is actually Sundargarh district of Orissa. So I think that a lot of effort is going on in that direction. Maybe things will be better. Even it can monitor the soil conditions. All types of things are being done. So I think there is a great future in these technologies. So thank you very much, Professor Manna. Now may I request Professor P.K. Nanda, our Pro Vice Chancellor of SOA University, to propose a vote of thanks.
Thank you, sir. Good evening, everybody. On behalf of INAE Bhubanewar chapter and SOA University and IMMT, it's my pleasure to propose vote of thanks. I'm extremely thankful to Professor Manna, who shared very thought-provoking, motivating, inspiring, and challenging speeches. And also he had a complete view of the synergistic approach to the real-world problems for survival of the humanity to the best extent. And also he lined up with the UN mandate, which has been kind of the thought of the whole concern of the whole humanity, and particularly the local in Indian context, how to match them. Also he highlighted. He also posed many challenges, also many eye-openers for our young people and also for the leaders, for the think tanks, and for this unsolvable to be solvable, and also many inspiring words that one should not be after success, it comes. It is very appealing to me, and many other, I think, very inspiring kind of the sentences and top-notch kind of the scientist history examples, and creating a better future, and which is augmented by INAE. I must share also, I agree with Professor Manna, and also share that he has linked the three technology and put in the best way that synergistic effort is the right answer, is the answer of the day, and we must unite together, and unity in the diversity is the best answer. And provided that the top-notch university of the world, they have in fact agreed to synergize life science, technology, science together. So similarly, Professor Manna highlighted the need for our country for innovation, where our Honorable Prime Minister has also housed where 40,000 innovation startups are already existing. Thank you very much, sir, for this eye-opener, for a motivating speech, and to be with us in this evening and the first lecture of this series. I thank Professor Damodar Acharya, who is the prime mover of this lecture series and the motivating force for all of us, and to carry this forward to a definitely better evening. Thank you everybody for participating, actively participating and discussing, and the takeaways are many. I wish all the best for everybody. Thank you, sir, again.
Thank you and namaskar.
Thank you so much. Professor Manna will increasingly depend on you.
Okay.
Thank you.
Thank you.
Thank you, sir. I would like everybody to open their cameras so that I can take some pics.
Okay.
Thank you so much.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you very much.
Okay.
Thank you very much.
So Renu madam, how many we had during peak period?
Sir, yes, we had 97, sir.
Pardon?
We had 97.
But at